In this screencast, we introduce the path frame. This is the second of our non-inertial reference frames. Our first non-inertial reference frame is the polar frame that we use in this class. And one thing that's unique about the path frame is that ultimately we don't care where the position of the particle is. We only care about certain information that help us define the velocity vectors and the acceleration vectors of the particle itself as it travels along the path. We'll start by defining our reference frames. We'll have an inertial reference frame, and then we'll define the path frame. In this example, our inertial reference frame is already given to us, in which we have an origin O for our inertial reference frame, and we have the basis vectors Ex, Ey, and then we need to add a vector Ez. And don't forget that your inertial reference frame, in the definition, if it's not given to you, must always be defined with the geometry of the system that you're analyzing. However, in this circumstance, when your basis vectors are already given to you, there's no need to redefine those basis vectors. So let's turn our attention to the path frame and define it. To define the path frame, we'll take advantage of what we know about any path. And we've said before that the velocity of any particle along any path is going to be tangent to the path. So we can draw the velocity vector, the velocity of p with respect to O as observed in the inertial reference frame. We'll add to this a frame in the direction of the velocity and have a basis vector, E sub t, that's always pointing in the direction of the velocity. And so you should see that as this particle travels along the path, E sub t, this basis vector, is going to change directions, and it's dependent upon the curvature of the path, or it's dependent upon where it's tangent. And so you'll see that this basis vector, E sub t, is a non-inertial basis vector because it's changing orientations dependent upon where the particle is on the path. So then if this is reference frame B, we're now defining our reference frame B, which has an origin at point P, and then we have our first basis vector, E sub t. The basis vector E sub t is always along the velocity vector, so we're defining it as the velocity of p with respect to O, but we need to make this a unit vector, so we're dividing by the norm of the velocity of p with respect to O as observed in the inertial reference frame. Let's define the second direction in our reference frame. And so here we'll draw our direction, what looks like down, but it's really a special direction, and we'll call this E sub n for our normal vector. Now what's special about this normal vector is that it's always pointed to the inside of the curve, or it's positive in the direction of the concave side of the curve. And so to explicitly define this direction, we say that it's perpendicular to E sub t, but we can't stop there because we have two options for that. It can either point away or up, as we're showing it here, or down. And so we define that even further by saying it must be pointed to the inside of the curve, or to the concave side of the curve. After we've defined E sub t, we've defined E sub n, we now have one vector left, which we'll call E sub b. This is the binormal vector. And this binormal vector will always be pointed out of the page or into the page because this is a two-dimensional class. But we're going to define the binormal vector as a cross product of our tangential vector crossed with our normal vector. Now one thing to notice about the binormal vector is that it won't always be pointing out of the page or always be pointing into the page. So don't be tempted to just say out of the page or into the page like we've done before. So for example, in the location that we see here of our particle, in which we have E sub t pointing to roughly to the right and E sub n pointed down, when we cross E sub t with E sub n, then we're going to get a vector, a binormal vector, pointed into the page. However, if we put this at a different place on the curve, where we have E sub t along the path, and then we have E sub n pointing in the concave direction, then E sub t crossed with E sub n gives us a vector that's pointing out of the page for the binormal vector. So our binormal vector will be flipping to be out of the page or into the page depends on the direction of the path, e sub t, and then, or tangent to the path, and then the direction of the normal vector, which changes based on the concavity of the curve. And one quick note about this is that what we just defined with a binormal vector is different than how the book presents this. They present another e sub 3 vector, but I want to eliminate any confusion between our normal use of an e sub 3 oftentimes in an inertial reference frame. Because of this binormal vector flipping back and forth, this does allow us to define this perpendicular vector to the plane as an e sub t crossed with e sub n at all times. So in our class, we're always going to use the binormal vector, e sub b. We're not going to use an e sub 3 like is presented in the book.